parentheses, E for exponents, and then the M and the D. Well, that's something that you can probably study yourself, which is a little trick to understand or to keep in mind or to remember so good the order of operations. And of course, for the division, the main condition is that you cannot divide by zero. Okay, that is impossible inside the world of the real numbers. Probably this will require that you create another world that contains the real numbers and solve the situation. And that's the advantage, right? That's the advantage of the mathematics, like comparing this one with other sciences. Mathematics can solve and can create and can make a very huge study field with situations that born in mathematics. That's the interesting part of it. Okay.
Good morning, Mr.
Good morning, sir. So here we can summarize this like the idea of keep the balance, in one equation, because one equation is working like a balance. If you're saying 5 plus 2 is the same as 7, it is because those equations represent the same amount. Okay, and that's like an interesting thing of in math. I mean, just that if we can represent like 5 plus 2, that is 7, I think it's better to say 7 instead of being saying 5 plus 2. So that's another idea. Okay, let's see how can we solve an equation. And when we solve for an equation, what we want to do is isolate for the variable. Well, if there is one, we will see some kind of equation. Honestly, it will not be enough time to explore like how to solve this equation, but we will see like how they are. We want to explore a little bit how to use the properties, and I want to ask you to try out. Just let me enable there he is. Yes, let me enable the drawings, and then you can start making anything you want. For example, I have here 6 plus 3 equals 9. So then what happens if I add like 7 to this side? Then I have to add 7 to the other one. So that's like the principle of addition. And the balance will stay the same because the same I'm adding here, the same I'm adding in the other side. So this is like the main idea of keep the balance. As you can see, both of the cases keep the same value. Here you have 16 and here you have 16. So that's like the main idea. Of course, we're going to do this with sense. For example, what will happen if one exercise, I just want to know what is 6. Suppose that I want to know just what is 6. What will you do? Ideas. I mean, I have 6 plus 3 equals 9. Using this equation, if I want to know what is 6, what can I do? Like divide by something, add something, subtract something, multiply something. It's like leave this one alone. That's like the main idea.
Then you would need to subtract 3.
Okay, you
From
probably
9.
will be subtracting 3 because it's like the one that's with the 6. And if I want to leave this 6 like with nothing over there, so if I subtract 3 over here, then I have to subtract 3 over there. And I think that, yeah, here, this expression becomes just like 6. And we can leave this expression like 9 minus 3, saying that 6 is the same as 9 minus 3. For what is going to be useful? Okay, probably another exercise. You know that one operation is equal to 6. Oh, here we have one. 2 times 3 is 6. So by the transitive property, you can remake this equation. And you can immediately say that 2 times 3, sorry, not the x, not the variable x, 2 times 3 will be 9 minus 3, because we know 6 is 9 minus 3. Will this be useful for the exercises? Okay, probably yes, probably not. Right now, I'm just doing random operations, okay? So the main idea here is focus in this idea of isolate one expression as we try it here with the 6. Okay, so those properties will be useful for this. But let's see it now with sense. Right now, I did it at random, like I told you. You can connect those properties however you want. For example, I don't know if someone wants to try like an operation with this one, with this equation, like add something, subtract something, whatever you want. With this one. 2 times 3 equals 6. Don't know if it's that you want to subtract or multiply or divide by something, this equation. Tell me, I will do it.
Divide by 2?
Okay, we can divide by 2. And if I divide by 2, the left side, which is a multiplication, then I have to divide by 2, the right side. Will those values keep the same equation? Yeah, we'll keep the equation.
Yes.
Yeah, of course. And
3
remember,
equals 3.
excellent. It's going to be 3 equals 3. And remember, an equation is a statement that gets a value of true or false. That's so important for the topic of equations, especially that right now we're going to focus not now in numerical equations. We're going to focus in algebraic equations. So let's see. So let's start with this first part. When you work with one algebraic equation, okay, I mean now you're going to work with variables. It's possible to get one or more than one solution for the expression. Okay, so here we go. The next part is how can you solve the next equation? Okay, there you have it. Ideas. Have you ever solved the equation? I think that yes, probably is that we didn't have like very clear that or very don't remember so good like those ideas. And let's see, I don't know. I just want to hear your ideas first. Like,
In this case, it would be like isolate the variable
excellent.
and move to the other side for 6. And then you will, since 2x is multiplying, then it will go dividing on the other side.
But how I move it to the other side? How's that to move to the other side? I like that rule. Honestly, this is a rule I normally use. But what happened? I mean, it has a meaning.
You need to start with the 6. Move like adding 6 on the other side.
6 on the other side.
Okay, okay. Adding
And then you
6 on
divide
the
it by
other side.
2.
And then, okay, I mean, that's the way. It's a two-step equation. I think you know that. Or you have been trying those. It's true. The way to solve it is simple like that. Like pass the -6 to the other side, you're saying. So in the other side turns the sign and becomes positive, right? Then you focus this addition. So then 2x equals 2. That's 24. And then you have the 2 multiplying. So on the other side, it's like you pass it to the other side, pass it to divide. Of course. From where this idea of pass to the other side comes from? No, any idea? It comes from keep the balance of the equation. And honestly, we normally don't use like pass to the other side to solve the equation. Just that this is a rule we create to make this job easier. Because the job you have to do to solve an equation will be like next. So first of all, objective is isolate the variable x. Leave alone the variable x. Eliminate everything around the variable x. You did it so good. Because here at the end, you have isolated the variable x. Sometimes the variable x has an exponent. So then you're going to need another operation to eliminate that exponent. So what we should do, honestly, this way is correct. Just that it's not the one focused on the property. So the one that is based on the property is starting with the 6. I mean, you were so good analyzing this with the 6, and it is especially because now you're going backwards. Okay, you're supposing that 2 times something minus 6 will give you 18, but you have to go backwards. It's not that you're gonna eliminate first of all the multiplication. No, that's gonna be like the last thing. It's like work PEMDAS, but like like that. okay, like going backward. First of all, you're gonna focus into disappear additions and subtraction, and then multiplications and division. And of course, at the end, exponent. Of course, if you have parentheses, it will be like the last thing to do. So as you can see here, using the principles of addition, that's why you have to add, you have to pass the -6 to the other side to add, because to keep the balance, I'm gonna add 6 in one side, I'm gonna add 6 in the other, balance stays the same, and essentially, -6 plus 6, okay, this is gonna be 0. But then, that 6 in the other side, if you see, is positive. Okay, so that's like the main reason. It is not because it passes and changes. I mean, that's the rule we create, and it's true. It's useful. Children understand that one faster than being doing all these procedure of the balance. But mathematically, it's based on that property, right? So at the end, we want to eliminate the 2. To eliminate the 2, if we have a 2 multiplying, the way to do and to eliminate it is divided by the same. Okay, so here it's why it's so important the number 0, for example. Why is so important the number 1? And if you remember the properties working with those, some of you mentioned this in the first forum, like the equivalent elements, okay? And the other is well, don't remember so good the name in English, but is the elemento absorbente in Spanish, and is 0, because everything that you multiply by 0 is 0, or every time you add two opposite things gives you 0. So those are like the main ideas. We're gonna use like the idea right now of the reciprocal expression of 2, which is 1.5, or just divide by 2. And immediately, if you divide by 2 both of the sides, you're gonna have the answer. So it's true. I told you again, as we teach, multiplying to the other side passes to divide. Okay, yes, it's true, but what we have to use essentially is these properties, or are those properties of keeping the balance. And as you can see, we conclude same answer. So I mean that we are correct. Now, what happened with that solution? It has a meaning for the exercise. You are requesting for a specific value of x that multiply it by 2, and then subtract by 6 will create 18. Of course, we suppose from the beginning of this variable expression that those are the same. They are not. But now, knowing that x is 12, they are equal. Okay, here you have 3 exercises. No, we have 2 minutes. Let's try it. Solutions. Use the method that you want passed to the other side, or solve it. If you want to share it, like writing over here, annotating, you can do it. If not, just like write the final answer next to the exercise or below it, or close to this one. I think someone already solved the first one. And the CSS says x equals 8 for letter A. X equals 8, you're saying. What about the other two? Oh, here you're having x equals 5. It's missing the one of the middle. X equals 7. Okay. That's so good. And well, here we have it. I think those are the solutions. Why we are 100% sure those are the solutions? I mean, why? You cannot say like, yeah, x could be 7 for this exercise, or x could be 5 for the first exercise. Idea?
We can, like if we solve it and we put the 8 for the x, like 3 times 8, like checking the answer to see if we get 18.
Excellent. It's like checking, right? It's just like checking. And it works behind the principle of substitution we studied from the beginning, okay? If in one equation we know, like, I mean, we can mix equations. That's what the principle of substitution we studied at the beginning is like telling us. So if we know here that 3x minus 6 equals the 18, then we know x is equal 8. We can replace the value of x by 8. I mean, the idea of an equation is find an unknown. So the idea of a variable is represent that unknown. And as you can see here, one variable can represent many unknowns, just that in the equation, it receives a constant. And that constant is telling you that it must be or it must get just a specific value. And in this case, is 8. For the other case, is 7. And for the last one, is 5. So variable idea, as you can see, because I'm using the same variable. I mean, if I use another one, yeah, then the same. But at the end, it's a variable. It's like getting many results, but represent these results in a specific situation. It got, or now it got a meaning. I mean, that's like the main idea with this topic. Okay, so let me clear those drawings. There he is. And we can move on to the next part, which will be talking about next idea. Is it possible to have more than one variable in one expression or in one equation? Yes. Okay, we can create like variable expressions equal to a variable expression, because right now we saw it that it works just with a variable expression equals to a number. Those are like two steps equation. Very basic case and very common case in the topic of equations. You're gonna see then why it's so important, the equations, but let's focus first in this case. Now you have variable in both of the sides. Don't know if you remember how to solve these ones now. Because at the end, equation topic is pretty interesting. This is like a new case, but then through some mathematical procedures, it becomes like the last case we try. Okay, so I think it's something that we can do very quickly. Don't know if someone can tell me like, how can we solve that one?
What I remember is
Uh-huh.
that we need to put together the common, how can we say this?
They
The
have a
numbers that
name.
have the common variable.
Okay, they have a name. We saw that yesterday. Don't know if, okay, if you remember or if you listen or if you watch the video. Because those that have the common variable have a name. Can someone tell me what's the name? Or remind Jenny, what is that name?
Like terms.
Lineal.
They are like terms. Excellent, like terms. So I'm agree with you, Jenny. What you want to do is like you move things to the other side and everything, which is that technique that we normally use in math. Is like get variables with variables and numbers with numbers. I mean, yeah, it's true. And it's logically like this, because at the end, I cannot operate 5x and 7. They are different kind of things. I cannot operate 3x and negative 19. They are different kind of things. So it's true. We're gonna focus over there. And we want to have variables one side, numbers in the other one. I think you know that. So the main idea is that, for example, here, we want to eliminate the expression. And if you remember in the properties, well, you can subtract both sides by the same or add both sides by the same. At the end, you decide how to do it. In this case, I'm gonna subtract both sides by the same in order to eliminate the 3x on the right side, in order to eliminate those like terms, but it will have, or it will affect the left side too. I mean, if I affect the right side, I'm expecting to affect the left side too. So here you're gonna have some like terms as we tried the last class. What matters over there is that you remember how to operate them. Don't focus in exponents at the moment to add or to operate like terms, okay? So here you have it. At the end, The expression that starts with variable on the left, variable on the right, now is just working one variable on the left, like the other exercises we already tried. So how can you solve it? It's pretty simple. Solve it, please. If you can show the procedure here, it will be good. Don't know if you get it, Jenny. That little name that you were like, yes? Okay, like term. Don't forget, it's gonna be useful for tomorrow test or quiz. Quiz, I mean. Like terms are so important in this context of algebraic expressions. So what would be the solution, or how can we get it? You're gonna add 7 over there. You can do it like this. It's through some books works like this principle, and then if you add 7 over there, you have to add 7 in the other part right here to this equation. What's gonna happen? Well, the equal stays the same, the equal stays the same, and it's like smash those equations. So the 7 and the -7 over here, they like cancel each other. They make 0. So then 2x equals 2. The result of this, -19 plus 7.
-12.
Minus 12.
-12.
Uh-huh.
Excellent. Now you have this equation.
So it's minus 6, right? You need
Yeah.
to divide it.
You need to divide it.
Divided to
It, you can show it here, like
Yes,
exactly.
minus. Uh-huh.
Mhm. You can show it here, I think.
So you need to,
Just, I
yes,
don't
the
know.
answer is x minus 6.
X equals -6.
Yes?
Oh, wow. Wow, very complete, Jenny. So good. There you have it. Jenny developed everything like one comment. It's through x equals -6. So you have over there like the ways to solve it. Here I divide by 2, and there is x equals -6. Okay, know that this way is one just that's working with some properties. The one that you say pass to the other side, it's good, but tends to create some confusion, especially at the moment when you have something multiplying and when you move it to the other side. Normally, students say, why it doesn't turn the sign? Why when you add and subtract, you turn the sign, but when you multiply, no. So it's a little tricky that way, but I think it's working behind the principle of the equations, and that's what matters. That we use, I mean, for didactics of mathematics in those last like 10 years, these have been changing. And instead of focusing more in the procedure, we focus more in the result because mathematics can solve in many ways, in several ways. Okay, let me clean this one. And I think we're almost like done with this first part of this topic. So good, like those participations. And that way, I think we can focus now in the last part. It's so important that once you get a solution, you check a solution. Probably in this context, it's not something that you need to do. Those are called linear equations with one variable. And well, it's so important. We focus here like at the moment we get a solution, we replace. And I think you know that. We already tried with the last 3 exercises. You solved so good. So if we substitute the value of x, the value of 6, sorry, instead of the variable x, okay, not the variable 6x, sorry, it's just 6. Over there, we're gonna have then like why this expression x equals -6 really makes true the variable equation we have over there. Because at the end, it creates, sorry, a true statement. Okay, a true statement. If we don't have this true statement, then this x equals -6 is not the solution. Simple like that. What does it mean? Okay, it means that probably the equation doesn't have a solution, or the more possible is that -6 is not the solution. But in this case, It is because it creates the equation works as well. And at the end, we can say that negative 19 is equal to negative 19 based on math basic principles. So I think the equation is so important. And well, I think you're so smart with a part of the equation. You don't need a lot of help. I just want to tell you that if we don't teach so good the basic operations, then it has the consequences. And what are the consequences of topics of equation? Okay, and look, this is not the topic of equation like the huge topic. It's just like the first part. It's just like the 1% of the topic of equation, I think so. Well, either the 1% is lesser than this, because at the end, the equations, well, using equations in physics, using equations in chemistry, using equations in biology, in other areas, you see that it has a big impact. So what are consequences in the same mathematics? Okay, first of all, there are many mathematics related with equations. This is the first situation. The second situation is that what you do with equation is model situation. Okay, create those phrases into math sentences. Like the last time we were working with some algebraic expressions, like Mark have the double of marbles as me. Okay, something like this will help you to model situations, and equations are like the best way to solve these situations. In algebra and in geometry, we're gonna work with equations, and of course, other areas like trigonometry and calculus, we're gonna focus in equations too. So the main objective of an equation, and listen this, because then it is not that just this type of equation exists. We're gonna see what kind of equations work. But the main idea is that, like in the multiplication of polynomials we studied the last time, if you know how to multiply monomial times monomial, it's gonna be so easy to multiply any polynomial. Okay, if you know how to solve linear equations, it's gonna be easy then to solve the other kind of equations, because this is the basic. And if you know how to solve the basic, the other ones, well, at the end, the other ones will work like with some procedures, some rules to be converted in these linear equations. As an example, here you have variables working as exponents. Okay, so how can you work variables working as exponents? Those are called exponential equations. And as you can see at the end, those exponential equations through some procedures becomes to be linear equations. That topic we are studying. As you can see here, here's more clear. You have 3 to the power of 2x. What can you do to free that variable x over there? Okay, there are some math procedures that work behind this kind of equation, but the main objective will be move all these situations to a linear equation that can be solved by passing to the other side or applying the balance equation. Okay, as you can see, it's like the main objective. So it has a big consequence in future mathematics, the topic of equation. Okay, so we're gonna focus now in the next part of this class, which is related with the type of equations. Okay, give me a second. I'm gonna open now the new one. Okay, here it is. And let's start. Okay, I think that you have been trying some of these ones, of course, probably not in our job teaching the children, but we must know what are like those topics that later they will study. Remember that here you're receiving like the fundamentals. So what are type of equations we will see? We're gonna see it. We're gonna describe a little bit those types of equations. We're gonna see like what will be the way to convert an equation into an equation with one variable. Okay, as we saw it, the main topic is linear equation with one variable. If we have these clear, then we can solve any kind of equation, just like following some new rules, and solve equations by the principles of linear equations, okay, with one variable. That's like another important idea. Equations with one variable. Okay, we're gonna see. So types of equations that we can work in mathematics, and I think the ones that you need to know to be sure about what will you teach, or to see like the consequences of your teaching process in these early years. The equations can be described by the amount of variables and the exponent they have. Who can remind me the name of the polynomial given by the degree? The name of the polynomial given by the degree. If it's degree 0, it has the name. If it's degree 1, it has the name, and so on. Gave you like a table in the presentation of yesterday that I will upload today. I don't know if you remember. Or Google it. Polynomial name by the degree. Do you remember? If it's degree 0, then it's called. If it's degree 1, it receives a name.
I just remember when it has degree 1, degree 2. When you have it 1, it's linear.
Linear,
Then you have
Degree 2,
quadratic,
quadratic.
Quadratic, cubic,
Quadratic,
cubic,
cubic, quartic.
Quartic.
Excellent. Quartic, quintic,
quintic.
and we can continue with more degrees, given like more interesting names. Yeah, so constant, linear, quadratic, cubic, quartic, quintic will be defining kind of equations. And I think that I want that you discover something interesting about this. So, basic case, linear equations with one variable. I think that we already studied this one with the last presentation, and I think you know how to solve it. Even if we have variables in both of the sides, at the end is just one variable working with exponent 1. Okay, that's why it's called like that. Linear equation with one variable. We have then quadratic equation with one variable. What would be like the main characteristic here? What do you think? In linear equation, exponent 1. In quadratic, what do you think?
exponent
2.
2.
Exponent 2. So it means if you see an exercise with exponent 2 in the variable, of course, it will be a quadratic equation. Cubic equation. So I think that if you understand the idea what happened with quadratic, with cubic, what you want is exponent 3, as is shown here in this example. And of course, these ones require interesting ways to be solved. Honestly, we're not gonna have the time to study those. And finally, in general, we can talk about polynomial equations, but just with one variable. If you see this part of saying one variable, one variable, one variable, it's so important. Because then if we work with two variables, okay, it will not be enough, just work with one equation. And it's something we're gonna see later. Of course, here, as we start with the numbers, that we cannot subtract natural numbers because the result is not natural, we're gonna be on the need to create new things, okay? Or new equations, new type of equations. Same idea, same principles are working here in order to make huge the world of mathematics. So let's focus on other situations. It's possible to have more than one variable. So what will you do in that case? To answer this situation, it will not be possible just with one equation. For example, if you have like two equations, you can create one system of linear equations if you are sure that those equations works with two variables, for example, or with more variables. You have here a little example. And this now is something new, because instead of being relating just one equation, you're gonna relate two. Don't know if you remember what are the methods that work behind this one. And yeah, in these situations, we're gonna have the same. I mean, linear equations, quadratic equation, cubic equation, polynomial equation, just that mix each other. So we have over there like first and basic topic we must know over here in each systems of linear equations with any amount of variables. Of course, if you have like 4 variables, you expect to have 4 equations. This is like the common part. Not always is like this. Sometimes you just have 4 variables and maybe 2 equations. And at the end, those probably have solutions, probably not. Okay, we're gonna explore this idea and we're gonna do something interesting too. We're gonna connect this part of the algebra with the geometry. We're gonna do it later when we talk about that geometry. So let's check it out. At the end, we can create two kinds of systems in mathematics, talking about the type of equation. We can talk about the systems of linear equations, okay, linear equations, and the systems of non-linear equations. The systems of linear equations are like the basic case of the systems of equations, because you relate like two variable expressions that work exponent 1 in order to create these relationships. We're gonna focus in these ones at the end. Honestly, I'm not gonna teach you all the topic related with that one. It will not be enough time. Just gonna give you like an example of how they work, but I will translate these to the part of geometry. You're gonna see how can we solve this one geometrically. And the other part is related with the systems of nonlinear equations. As an example, here you have one. X squared plus y squared equals 10. Is not a linear equation because you're working exponent 2 and exponent 2 over there. So that's a quadratic equation. This one, y equals x plus 2. Okay, this one is a linear equation because you're having the variables with exponent 1. So the main idea with this topic is like use some principles that we studied at the beginning, like the substitution principle, the transitive property, in order to solve this one. Of course, the ones that keep the balance are useful every time. Every time you work with equations, the ones that subtract in this side and subtract the same in the other will be useful every time. So those are like types of equation. Is it possible to be bigger? Yes. But then with this one, we go outside of the mathematics you need to know. We can go to the other one, okay? We can go to the word of the, how can I say in English? A las matemáticas anilladas, a la teoría de conjunto, a la teoría numérica y al análisis real. Y eso ya es otro contexto. Así que sí se hace más grande y todo va surgiendo porque con un ejercicio surge un pequeño problema que no se puede resolver. Entonces, hay que inventarse la solución para inventar, pero para inventarse la solución, como vimos anteriormente, hay que crear un nuevo mundo de matemáticas. Y así surgen nuevas matemáticas. Eso es lo bonito de las matemáticas. De hecho, una que ha surgido estos últimos años es en geometría. No, mejor en geometría hablemosla. Me gusta combinar mucho las cosas y lo voy a enredar. Mejor hablemos de ecuaciones ahorita. Ya lo vamos a ver luego. So those topics open the need of new strategies and algebraic techniques, I was saying, to be converted into a linear equation. Of course, that's like the main objective. Look for the way, as you can see here, the development of this exercise to convert this exercise in linear equations. At the end, you have here a simple linear equation. The simple linear equation, honestly, is not this one. It's x plus 3 equals 0, x minus 1 equals 0. And then x equals -3 is the solution of that linear equation. But at the end, if you know how to solve linear equation, which is the main part, students will have the tool to understand these weird exercises, okay? That probably describe situations in real life. But with systems of linear equations, it's more possible to model things of real life. So here you have a linear equation example too, and I think probably you remember this. Who can remind me like what are the methods you use to solve these equations? Don't know if someone remembers. Or you can Google it, methods to solve systems of linear equations. There are like 4 methods. Normally on internet and in the books, we just find 2.
The graphical method.
The
I got
graphical method.
six most common. Graphical, elimination,
The substitution, the one
substitution,
that's working with
cross multiplication.
which require that you work with matrices. And with this topic, we open now, wow, new mathematics. Have you ever heard about the matrices in mathematics? Not the movie, the Matrix. I mean, for example, for Google or for for Facebook, well, now it's Meta, right? Meta, that's the name. Meta, ahora sí se llama, ¿verdad? Ya no se llama Facebook, se llama Meta. Creo que, bueno, ahí está una noticia. Bueno, ahora en Meta, nosotros no cambiamos lo que hemos sido para Meta. Nosotros solo somos una información en medio de dos paréntesis. Somos un arreglo, una matriz, en donde cada valor que asume una posición tiene un sentido. Por ejemplo, el primer valor, ok, su correo. El segundo valor, ok, su contraseña. El tercer valor, su nombre de perfil. El cuarto valor, etcétera. Ok. So at the end, for all those industries, we are matrices. Simple arrangement of numbers, but those numbers will get us there. Okay. Talking about linear equations. So linear equations are like the basic way you can understand an equation. And I think those can be solved by balance principles we saw at the beginning. Linear equations can practically work with one variable or more than one variable, but this one will have degree 1. You can work with x plus y plus z equals 20, for example. That's an equation. But all of they have degree 1. That's like the main characteristic. And that's why they receive the name of linear. Here you have an example. I think we have been trying some of these ones. And of course, you can get the solution. One important idea. For this type of equation, it's possible to get, listen, at least one solution, at least one real solution. What means at least? At least one real solution. What do you think means at least one real solution? That probably there is no solution. No?
Yes,
That
we
the
can
answer
get
is
one.
positive.
We expect to have solution or no solution, but if it has solution, we expect to have at least one solution. Now, why I'm saying at least over there, it means that we can have more. And it's true. In a determined moment, some linear equations create something irregular in math. And instead of just have one solution, which is the common thing, because the degree is 1. So copy that. That degree tells you the amount of solutions you expect to have from one equation. If it's linear, degree 1, okay, one solution. If it's quadratic, degree 2, okay, 2 solutions. But that's what I'm expecting. Now, it's not that's normally like this. Sometimes it have more than one, sometimes in this case, we have like 3 chances, to be honest. We have the chance to not get a solution. We have the chance to get the solution. And we have a chance to get infinitely many solutions. So these are like the 3 cases that works behind linear equations. Okay? Not get a solution, get one solution, or get infinitely many solutions. Because sometimes these variable expressions doesn't create a statement that is true, or create a statement that is true for every number you choose. For example, if I ask you right now, what will be the result of x plus x equals to 2x? What will be the value of x? That makes this true.
One.
Okay, 1, yeah, 1 plus 1 is 2, and 2 times 1 is 2. What about
It
5?
could be any number.
Okay.
No, not any number. A ver.
Yeah, you say it, any number.
Any number.
Yeah. If I choose 5, 5 plus 5 is 10, 2 times 5 is 10.
Oh, yes.
If I choose negative 20 plus negative 20, that's negative 40. 2 times negative 20, negative 40. So any number. It's so hard to see these, but it's so important. We know and keep in mind that. And again, degree 1 is telling you that you expect to have one solution, but not always is like this. Okay, there you have it. I think we can explore the next one, or a little bit this one. So I think we can solve these equations pretty easy. We already know how. For example, here we expect to have like one solution, so let's get it. Passing the 60, I think we already tried that one, right? No?
No, it was a different one, but
Okay. So x equals 2, tell me then.
it would be 24/5.
It's gonna be a, it's gonna be a like a fraction. It's
As a
true.
fraction, it would be 4 and 4/5. X equals 4 and 4/5.
I mean, you have it like a mixed fraction. Oh, that's so interesting. So it's true. I think here we have x equals, you pass the 6 to the other side, starting, so it's gonna be 24/5, right? It will be like this. It will be okay like this. Okay, you can write as a mixed number too, no problem, which is 4, 4, what's the number you say? 4, and then 4/5?
Yeah.
Yeah, okay. So you can write it like that. Now, what will be the solution of the second one? What will be the solution of the second one? That's so good. You're trying to move to the other side or using the balance equation property. Gonna summarize this a little bit. If you see on the right side, we have some like terms that we can operate. So I'm gonna operate those like terms to see this simpler. You have 2x plus 4 equals 2, okay, 2x minus 9. So what will be the value of x over there?
X equals -13.
X equals -13. Okay, I see some people and were making like, not agree with you. In the chat, can you say it doesn't have solution? Okay. Why you can say that it doesn't have solution? Working variables with variables, numbers with numbers, you're gonna have next. You're gonna have 2x minus 2x, -9 minus 4. If we see this, then we're gonna have 0 equals -13.
13.
So it's not that -13 is the answer. No, check this out. Are those
It's
things the
not.
same? Is that statement true?
No,
Okay, so no solution.
no solution.
That's why it's so important. Yesterday, I told you focus a lot in that when we talk about an equation, we talk about a statement and we expect to have this statement as something that makes it true. Okay, makes something be true. But right now we conclude something that is not true. I mean, 0 is not equal -13. It's true. So here you have it. What about the last one? What about the last one?
The last one stays like 3x equals 3x or x equals x. So I'm not sure if that means no solution too.
Okay. And it's so good because yes, here we have like the 3 situations I told you with this example. So gonna simplify this one in order for
One
you
would
to
be
show.
0 on both sides.
Okay, it will be 0 on both sides essentially. Working the like terms. I'm gonna work here 3x and here I'm gonna have 9. Oh, practically I have the same in both of the sides. So at the end, this passing to the other side and everything, you're gonna have 0 equals 0. What means 0 equals 0? Now, check the difference. Here we conclude something that is not true. I mean, that's false. But what happened here? It's 0 equals to 0. It's 0 equals to 0. I mean, is that a true statement or a false statement? That's a true statement. And what happened if it's true? Okay, here comes like the interesting part. You cannot say that X is one value. X can be any value. There is a big difference between those. Here, we are 100% sure this is the solution. Here, we are not sure about the solution of this one. Probably, listen, probably with this situation, we will be on the need of create new mathematics to look for the answer of this situation. Okay? Okay, let me tell you those already exist. And instead of work with equation, we work with inequalities. And there is the way to solve this kind of situation, of course, when you work with inequality. So at the end, we have here a representation of the three cases. When you have like one solution, when there's no solution, and when you have infinitely many solutions, okay, or just many solutions. Many as you can, because any real number can be chosen as the X value, and you're gonna have the result over there. So you have over there these three examples, so important you understand like what's the main difference between them. Any question about this one? No questions? Okay. For the quadratic equation, for the cubic equation, for any polynomial equation, we must focus on next. The remainder theorem and the factor theorem, those goes like together. And honestly, those are a little related with what you did, with the job you did, investigating for the synthetic division. The zero product property is one of the most useful properties to solve any polynomial equation. And of course, factorization techniques. We will not have time to explore all those factorization techniques, but I will share to you a video that will help you to explore them. Okay, I'm gonna focus just on one, which is probably one you remember so good, guess and check, or in Spanish is tanteo y error. I don't know if you remember this one, or a little bit like what's the main idea behind it. If not, we're gonna try it. Okay. Let's start with the principles now that will help us, listen carefully, to convert a polynomial equation into a linear equation or into many linear equations. One question, what happens if I have next equation, sorry. What happens if I have like x to the power of 5, I don't know, plus 20 equals to 100. How many solutions do I'm expecting to have? How many? Can you say it?
5.
5, right? I'm expecting to get 1 solution, 2 solutions, 3 solutions, 4 solutions. Well, 5 solutions. Probably it's not that always I'm gonna have 5 solutions. No, it's probably I get the 5. Probably I just get 4. Probably I just get 3. Probably I just get 2 or just 1. Or well, maybe there's no solution for the exercise in real numbers. But this is something that we have to keep in mind. That degree tells us the amount of solution we're gonna have. Okay, this is like first thing we have to consider when we talk about polynomials. Okay, now that if we remember and keep in mind this idea, then we're gonna be clear about what happened with this kind of exercise. Solving a polynomial. When you talk about polynomial equations, factor and remainder theorem are interesting and useful at the moment to use this one. For example, the remainder theorem tells you that if the result of a division okay, is 0, then the divisor and the quotient, the divisor and the result, both becomes the factors of the expression that you were dividing. What is this in symbols? Okay, if you have P divided by Q equals P, remainder 0, then P, which is your dividend, it's equal to the product of the divisor and the quotient you get. A little example. You can try it with the synthetic division if you want it. Okay, I think you're clear how it is. The remainder will be 0. And if the remainder is 0, then immediately you know that x minus 7 and x plus 3 becomes factors of x squared minus 4x minus 21. Of course, it's something that we work in the divisions too. I mean, if I have 12 divided by 3, what's the result?
Four.
4. Excellent. Why is 4? Because 12 can be written like 4 times 3. Same idea here, just that we are working with polynomials, of course. So, is this so important? Yeah, this is like the most important part because as you can see, what happened with the exercise? This is like the exercise. What happened with this exercise? That is x to the second power. I mean, suppose you have the exercise like this, x to the second power minus 4x minus 21. And if you say use the quadratic formula, it's because you're already familiar with this type of equation. It's true, but how can you solve this one? I mean, with the principles we have been working until right now.
Factorization.
You're gonna apply factorization. Okay, now you're using that technique. And it's true, you can factorize. But with this idea of keep the balance, can you solve it? Like passing to the other side, can you solve it like this? I mean, there will not be a way then to join x squared with negative 4x because they are not like terms. But if you check this now, if this expression, if this one, that now becomes, instead of word like x to the second power, which is, I think, the main problem, becomes like x plus 3 and x plus 7, something simpler by the factorization, like you say, or by the remainder and factor theorem, then we can solve it. I mean, then the exercise becomes like x plus 3 times x minus 7 equals 0. Okay, probably with this, we're going to have now an easy way to solve it. Just that's not clear. What can you do with this? Don't know if someone can tell me what happened when you have like something multiplying, another thing multiplying, and this gives you 0. Can you tell me what happened over there? I mean, if I have, I don't know what number times, I don't know what other number, it gives me 0. What can you say about those squares, about those little boxes in here? Okay, what you can say is that probably, we don't know which one, but at least one of those have to be.
One of those has to be 0. because
Excellent.
Any number multiplied by 0 will give us a result of 0.
Excellent, Tiffany. I mean, and it's a logical situation too. If I'm multiplying two things and the result is 0, it is because one of those is 0. Okay, let me tell you that this property receives a name, and that's the zero product property. Okay. The zero product property tells you, okay, if the product of two expressions or the product of two numbers is 0, the result of this multiplication is 0, then one of both is 0, or you can immediately say that both of those are 0 because you don't know which is the one, as we have it over here. And that's so important that we use the word or. Because we're saying that probably is one of both or both of the values at the same time. So here you have the example. Exercise was x squared, just to show you, x squared minus 4x minus 21, I think, equals to 0. it becomes, by some procedures, some new rules, some new strategies, into the product of two what? What's the name of this expression? What is the name of x plus 3? What kind of expression? Checking the degree, checking the amount of terms. What is the name it received? Do you remember?
Factor.
Linear.
It's linear. Okay. It becomes now a linear, okay, linear binomial, but it's okay if you say linear. It becomes a linear expression. What happened with linear expression? Hey, there are linear equations at the end. And if you see, what you did is convert this exercise that probably doesn't have any sense into two exercises that you can solve with those principles. So what is the topic of equations about? Every time you see a new kind of equation, what will be the objective? Convert it into a linear equation that you can solve just by passing to the other side. Every time is going to be like this. And as you can see here, if I ask you for the solutions of x squared, and listen, the solutions, not the solution, the solutions, because this is second power, then we expect to solve for x in both of those exercises. X plus 3 equals 0. X minus 7 equals 0. Solving for those, you have the solutions of the exercise. So pretty interesting, right? I don't know if you see those details before, but it's something important. What happened if that degree is 3 then? What happened if the degree is 4? Same idea, okay? So the next part is related with the factorization method. Honestly, I'm just gonna focus in one. I let here this YouTube video, it's like 11 minutes. It explains very quickly these methods. I will focus on this, okay? In the test, I will focus in this one, the guessing and checking, which is related with this kind of exercises, okay? Because I'm gonna focus in two types of equations for the test too. But I think that we must keep in mind and have a clear idea of how these polynomial equations can be solved. That's so important. The topic is pretty huge, honestly. To see it like in 2 hours is not enough. To see it maybe in 7 hours, yeah, probably over there we're gonna study all those factorization methods, the special product techniques, the greatest common factor idea, but okay, we don't have that time. And what matters to me is that you have a clear deal, that if you have a polynomial equation, the objective is convert it into a linear equation and solve it. Well, not just a linear equation, many linear equations as the degree you have. So talking about the quadratic equation, any quadratic equation, we have the x to the second power. Then if you don't have the rest, no matter, but you must have this x to the second power. Without this, it is not a quadratic equation. That's why you have over there a little condition that says a is not 0. A can be any other real number, but not 0. Because if a, which is the coefficient of the x squared, is 0, x squared disappears. And if it disappears, it's not a quadratic equation. Okay. Here's an example. X squared minus 5x plus 6 equals to 0. And how can we solve these exercise? For these types of equations, we expect to get at most 2 real solutions. Now, what means at most? Different than the last time I say at least. Now I'm saying at most 2 real solutions. What means at most 2 real solutions? That probably I get 2 solutions.
But with that 2 solutions would be like enough to see what is the value of that variable.
The values for x.
Okay. But if I ask you, go right now to your kitchen and look for and bring at most 2 glasses. What will you do? Si les pidiera ahorita que a lo mucho trajeran dos vasos.
No
Ahí
more
sí,
than
sí.
2. Then.
No more than 2. And what numbers are no more than 2? Okay, I'm talking about 1, 0. Okay, so what I'm trying to tell you here is that in these cases, if we expect to have like at most the amount of solution as that degree tells you, you can have 0, 1, or 2, and that's it. Okay, what happened if the degree is 3? Okay, you can have 0, 1, 2, or 3 for cases. It's a little different than the linear equation. Okay, linear equations are so special in real numbers, of course. In other contexts, they work different, but that's like the main idea. Don't know if that point is clear. And that's why linear equation becomes to be like the base of every equation topic. So let's focus a little bit on how to solve this one. So how can you convert a quadratic equation into linear equation? Factoring methods can be useful. Here you have another way to do it, which is apply the quadratic formula. Don't know if you remember this one, probably yes. I think it's so common that in topics of algebra, you study this one, negative b plus or minus the square root of, I don't know if you remember this one, b squared minus 4 times a times c divided by 2 times a, where a, b, and c are like values given by the general form of a quadratic equation. So here, for example, a is 1, b is -5, c is +6. Okay, so those are like main ideas. But you can use this property, okay, the quadratic formula, and it's useful just for quadratic equation, or apply factor and remainder theorems. Of course, this will require that you apply a general way to solve any polynomial equation that is called the root-finite method. Okay, we're not gonna have the time to study this one, but here you have one example. How can you solve this equation then? The main idea is how can you convert this one into a linear equation or into linear equations? Well, gonna use factorization method. And the way I do these is by using the method that is called guess and check. And for this one, you have to focus on the x squared, you have to focus on the 6, and then decompose them. How can you decompose the x squared? There's just one way, x times x. How can you decompose the 6? Okay, you can decompose the 6, well, in this case, +6 in several ways. Not many. There are like 4 or 5 way or 6 way, I think you can decompose it. Who can tell me one of those? Like 2 numbers that multiply gives you 6. I don't know if you remember that topic. Ese es tanteo y error. 2 times 3, okay, and you're getting like the ones that works for the exercise, right? Is it possible to work with another combination?
6 times 1.
6 times 1, exactly. Is it possible to work with some more?
3 times 2.
3 times 2,
by
yeah.
inverse.
Yeah, okay, it's still being like the same, okay?
Can we do like adding 3 plus 3 or just multiplying?
Just multiplying. Remember that when we say decompose, it's related with multiplication.
Okay.
Because that's a common error too. Think that you can decompose this one like by addition. It's not. So are just that's the only way. I mean, 6, +6 can be written just like, think in real numbers. 6 times 1, I agree with you, or 1 times 6 is the same. +6 can be written like 2 times 3 or 3 times 2 is the same. Is it possible to do it other way or not?
Yes, -2 times -3 would give us 6.
Excellent, Tiffany.
I remember that topic now.
Excellent, Tiffany. I mean, do not think just in positive. Negative numbers can give us a positive number too. What about -3 and -2 or -2 and -3? Okay, honestly, those are the ways, the factors we need to keep in mind and moving to factorize this one. And as you can see here, you can consider both positive or, well, you can consider both negative. And for this case on the exercise, if we consider both positive, sorry, it will not work. It will create a big problem. And that problem is that it will not get or will not give you the value that is exactly in the middle. Okay, so we're gonna solve this situation, just eliminating those. And what I want to show you is like what happened if you try it like this. Okay, what happened if you try it like this? That's why those are positive. Then we're gonna return this one, no problem. What happened if we try it like this? If we think that those are like the factors or the elements that will help us to construct the factor. Decomposing these, we have here several ways, four ways, as I told you. Well, I said 6 are 4. And if we check this, that's why it's called guess and check, because you guess this is the combination that will make the factorization, and then you check it. The way to check it will be like multiply those expressions linearly. And here you make positive 3x, and then you make positive 2x. If you operate them, because then the next part is check solving this result that I get by multiplying this way. I see that this gives me 5x, but it gives me positive. But if you see the expression between, which is like the one that's telling you at the end, if your guessing and checking is correct, it's not positive. It's negative. Okay? So what we want to do then is not focus in those positive values. What we want to do then is focus in those values, but working negative. So let's change this one into negative numbers. And at the end, you're gonna see like, what are the solutions? Because if you decompose this one in the correct way, then you can apply that zero product property, the part of the properties that I told you works like this. And working those negatives, now I think we can get the answer. So that topic of guessing and checking is pretty interesting, and it's pretty easy. And as you can see now, we get the -5 in the middle. The combination we were looking for is this one, and it is just 1, because the factorization of the exercises is unique, and all you have to do is mix them. Okay, you're gonna mix. Let's change the color, blue. You're gonna mix this one, sorry, give me a second. This x with this 2, with this -2. So you're gonna create the next expression, x minus 2, and this x with this -3, and you're gonna create then the other expression, x minus 3 equals 0.
Can you say again, why are you crossing them? Why?
Okay,
why
this is just like copying. Honestly, this is the question I was wondering you do. This is something that I decided to do. In other books, what you do is like cross them and multiply them to see if they make the number. I don't decide to work this one this way. I decide to operate them linearly. It results to me easier, I think, to see. And then to copy the answer, you have to cross it, because probably not in this kind of exercise, probably in other exercises, like when you have like a number at the beginning, it will change the result. Right now we don't have, well, we have a 1 at the beginning. We don't see it, but there is a 1. Just my recommendation is try to make like, okay, I call it like this, sorry, it's the way I teach. I call it like the scissor method, because at the end you make a kind of scissor over there. And you relate this expression with this one and this other one with the other one in order to create the answer. Okay? Just in order to build the answer, to construct the answer, just for that reason. And why you're saying, yeah, but this x is the same as this other one. Okay, what will happen then if you have another exercise that behaves like this one? I want to show you like what's the difference. X minus 3. Suppose this is the answer of one exercise. This exercise was like 2x squared minus 6x. Don't worry of what I'm doing right now. Don't worry about it. Just that I want to show you what happened with this. Exercise is 2x squared minus 5x minus 3. Okay, that's the exercise. Look from where this comes from the product of those. It means that this 2x plus 1 and x minus 3 is the factorization of this one, right? So let's get it. Let's find it. Let's find it out. If I ask you to guessing and checking right now, and I think that it would be a good exercise, this one, to try this idea. 2x squared minus 5x minus 3. To solve this one, equals 0. To solve this one, we have to focus in to decompose the first expression. If you see, I choose easy numbers to get the answer very quickly. So, and it's a little similar to this one. So how can I decompose 2x squared now? Not x squared. 2x squared. How can we decompose it? Idea? I mean, x squared, x and x. But the 2? There is
X.
just one way.
X times 2x.
Excellent. X times 2x or 2x times x, the same. Now, how can you decompose the -3? There is just one way to. Now it's negative, not positive. Tell me, two numbers that multiply gives you 3. I mean, there is just like one combination.
3 and 1.
3 and 1. Excellent. Now, because it's negative, one of those has to be negative. Which one? It's not like in here. It's positive. Both are positive or both are negative. But here, the -3, wow. It had to be negative, one of those. Which one?
3.
The 3? Okay, you can decide. I mean, you are guessing is the idea. Let's check it, okay? If I check it, I'm gonna multiply it this way, and then to build the answer, I'm gonna make like the kind of scissor you see over there in the other exercise, and then see the importance of doing the scissor, okay? Do you remember what was the answer? Did I show it here? Don't know if someone copied it. No? Okay, we're gonna see it. So checking this, the product of 2x and -3 is -6x. The product of x and +1 is +1x. If we operate -6x and +1x, the result will be -5x, the expression between, which means I can build my factorization with this element. Now, what's the factorization then? If you decide to work the 2x with the -3, and then the x plus 1, okay, let me tell you that you're solving another exercise, not this one. But if you respect the simple idea of make like a kind of scissor with this expression and get the next result, 2x plus 1, which looks a lot different as you can see, you're solving the exercise. So that's my main reason of why I do it like this way. I'm gonna show you like what's the result of this one. If you apply distributive property, you're gonna have 2x squared. Okay, nice. It's like the first number we have over there. Then 2x times 1, it will be 2x. Then -3 times x, it will be -3x. And -3 times 1 will be -3. If we operate this, if we solve this exercise, this factorization is the factorization of 2x squared minus x minus 3. As you can see, it's not the same. Okay? So that's why I do this thing of apply like a scissor. I think we don't know how a scissor is.
Okay,
And
thank you.
that way, yeah, welcome. And that way, I think you can conclude this so important and it's gonna be evaluated. So please keep in mind how to work this method. Simple as focusing, guessing, and looking for the correct combination. At the end, this becomes like a puzzle game. Don't know if you like puzzle games, but at the end, this becomes like a puzzle game, okay? So and that's like the main idea. Be careful with this kind of exercises. I mean, this is not the only way you have to factorize by guessing and checking. Other books propose other ideas for guessing and checking. And of course, once you have clear the guessing and checking procedure that you will use, you're gonna get the factors you're going to need to solve the equation, okay? Because at the end, that's what we want. We want to solve the equation. I think we're gonna have these expressions over there. And what an interesting question. Honestly, I was wondering for it. But again, it's like the way I do it. It's the way I decide to do it. You're gonna find probably other ways in the book, in the books or on internet. So then, like I was saying, x minus 2 times x minus 3 equals 0. And what does it imply? Okay, it implies that x minus 2 is equal to 0 or x minus 3 is equal to 0. Why I can conclude that? Can you remind me? Why I can conclude this? Why I can convert, or why I can become from this expression to this one? Can you remind me why? What was the name of the property?
The zero property.
The zero product property, okay? They can call it like the zero product property. There you have it. And by the zero product property, now you convert your exercise that at the beginning was working with x to the second power, a quadratic equation, into two linear equations that can be solved just passing to the other side. I think you know what is the solution. X equals 2 or x equals 3. Okay, so at the end, here you have a method, and I hope that you get like the main idea of guessing and checking. If not, then you're gonna have the YouTube video. On the YouTube video, the guy who explained the topic did it or do it practically focusing in this kind of expression. Okay, but focus more in the guessing and checking, which is the one I will ask you to try and like get the solutions. Wow. Bueno, lo siento por el ruido. Ok, bien, estamos entonces a 3 minutos para el break, porque sé que cansa un poquito estar viendo la pantalla, hay que estirarse un poquito. Así que les hago la pregunta, así como el sábado anterior, si quieren que tengamos solamente 15 minutos de break, o los 30 minutos como estaba propuesto, y terminamos 15 minutos antes. ¿Sí? O sea, sería el break de 10 a 10 y 15, y terminaríamos entonces una hora después a las 11 y 15 ya con la última parte de geometría, porque esto sería lo que tenemos que profundizar en la parte de ecuaciones. Lo siguiente es de sistemas de ecuaciones, pero aquí nada más es mostrarles cómo funciona. Vamos a resolver uno, no con los métodos que aparecen acá, que son el de sustitución y el de eliminación, que de hecho estos los pueden encontrar online con la página que sugerí la vez pasada, que se llama Symbolab. Lo pueden hacer perfectamente ahí. No les voy a pedir que resolvamos sistemas de ecuaciones lineales, pero sí quiero que veamos qué significa resolver un sistema de ecuaciones lineales. Porque al final, si ustedes se fijan, el mismo proceder. El objetivo es convertir un ejercicio que tiene 2 variables a un ejercicio que tiene una variable y es lineal. Sencillo. Siempre es el mismo objetivo con el tema de ecuaciones. Llevarlo a un sistema, perdón, a una ecuación lineal con una variable. Bueno, lo vamos a ver cuando volvamos del break. Nos quedamos acá. Y así nos vemos entonces dentro de 15 minutos. Bueno, no son exactamente las 10, pero les puedo ceder estos 2 minutos, no hay ningún problema. Así que a las 10 y 15, para que terminemos entonces, a las 11 y 15, recuerden que al volver ahorita a las 10 y 15 voy a chequear asistencia, así que por favor, atentos y atentas. Bueno, volvemos. Ahí si se me olvida grabar, Mauricio, me recuerda, por favor. Vamos a pausar el video ahorita.
Okay, mister.
Ok. And I think we can conclude this part of the equation and then focus in the last part of geometry. The last part of geometry will be something of us. It's not that I'm gonna propose it. I'm gonna propose questions and you're gonna be participating over there. So try to participate, please. So the last part of the equation, talking about the systems of linear equations. We're not gonna talk about systems of nonlinear equations. Topic I think that students study in those years is, and this is like one of the highest topics, systems of linear equations. So in what consists, what is a system of linear equations? A system of linear equation is practically relate one group of linear equations, okay? And the situation is that normally those linear equations work with more than one variable. That's like one of the conditions that happen in here. It's so common to see this kind of situation in this topic. The systems of linear equations will arrange the numbers and the variables practically following the principles of linear equations. What are those principles of linear equations? Okay, for example, the general form of a linear equation is that you work the variables in one side and the numbers in the other one. Things that we were applying in the other exercises, okay? Systems of linear equations can solve just by one equation. That's another problem. The systems of linear equations will require that you solve this one, focusing all the equations that works for the exercise. The systems of linear equations can be systems of 2 times 2 if you work 2 variables and 2 equations, or can be 3 times 3 if you work 3 variables, 3 equations, or, well, in general, n times n. Okay, normally the same amount of variables is expected to be as the amount of equations. Not always like that. So those are related with matrices, I told you. And at the end, there are like 4 ways to solve this one. I want to show you like 2 ways, but first of all, let's talk about the solution. Differently than in the other cases, when we solve for x and we get like 1 or 2 values for x, in this kind of exercises, we want to get a combination of values. Have you ever seen this x and y before? X comma y before? Where do you see it? Can you tell me?
With the coordinate planes.
Excellent.
When
Coordinate
you're like
plane.
making graphs, right?
Exactly. When you make graph,
Graphication, algo así, no sé, se llama.
yes,
Yeah.
it's true. When you're plotting in the coordinate plane, essentially it's like that. X comma y can be considered as a point in the coordinate plane. It receives the name of an ordered pair. And what you have over there is a combination of 2 values, specifying the first position for x, the second position for y. This is an arrange of values. This is a little matrix. But at the end, it's not a matrix at all, because we'll not work with those principles. Just work with the principle that the first value you represent is an x value, the second value you represent is a y value. Of course, here you want to have 1 value for x, 1 value for y. And why just 1? Why just 1? Why do you think it's just 1? I mean, why I will not focus in have 2 variables, 2 values for x and 2 values for y? At the end, the linear equation requires 2 values, but specifying that 1 is for x, 1 is for y. So why just 1? How many solutions does a linear equation have?
1.
Okay,
Only-
that's why. Because we're working about linear equations, we expect to have 1 solution. Well, probably, listen next, the system of linear equation will have 1 solution, which will be an ordered pair. I don't know, 5, 2. This will be the solution. Or probably it doesn't have solution, or probably it has infinitely many solutions. Okay, as we started with the linear equation, the same happens with the systems of linear equations. So we can have at least 1 ordered pair as answer, or probably not, or probably infinitely many ordered pairs as we can. Okay, an ordered pair is simple an arrangement where x values and y values are related with real numbers. We're gonna see these in the part of geometry, you're gonna see it. And at the end, this is summarized like the solution, okay? The x value and the y value that will together, those solve the system of linear equations. How can you see if the system of linear equation is solved or not? Okay, you can replace those values at the same time, the x and the y in both of the equations. So you should try this one and tell me then which of these 4 options is the solution of the system of linear equation. I think it's something that we have been trying. I'm not asking you to solve the system. I'm just asking you to find the solution. How can you do it? Okay, we already saw how to check one equation with one variable. Now we want to do it, but with two variables, specifying that first value is for X, second value is for Y. So what's the solution? Don't know if you're trying, if you're replacing the value of X in both of the equations to see if it works, and the value of Y.
Is it option B?
Why is like that?
Because you have to substitute the values. So in this case, X will be 2 minus Y will be 3. So you do.
It will give you -4, right? Let's see if that's true. I don't know. Remember, at the end, an equation is a statement that will get a value of true or false. What we want to do is look for the value that makes this statement be true.
So you
So let's,
multiply that, right? -2 times 3, that will be -6.
is 2 minus 6 -4? Of course it is. Now,
Option C.
it works for this one. Let's see if it works for the other one. I don't know. I'm going to try the option B first. Just remember that is unique. If this is the answer, well, then it will not be any other answer because it has an answer, one answer, no answer, or, well, many answers. So would you check it with the first equation? You have to check it with both. 3 times 2 plus 3 equals -4. Sorry, equals 9. Not -4, sorry, it's 9. Second equation, right? Does it work for this one?
Yes.
It will be 6 plus
6
3,
plus
come
3,
on.
9.
9
And then
equals 9.
close to 9.
Excellent. What you see over there is that you solve the system. And of course, it must work for both of the equations. Okay? If just work for one of the equations, okay, no, it's not solving the system. You have to work for both of the equations. So immediately you can say that's the solution. Why is not -3 and 2? Okay, -3 and 2. I'm gonna show you just with the first equation probably. We will see that's not working. Here you're gonna have -3 for the X minus 2 times that 2 over here. It will not give us -4. You're gonna have -3 minus 4. That's gonna be -7. So at the end, you're gonna have -7 equals to -4. As you can see, trying with this one, no solution. It's not the solution. You're gonna have something that is not true. Okay? You have a false statement, and wow, it's not what we want. What we want, it's a true statement always, every time. Okay? So as you can see, if you have the possibilities to get the solution, you can find it very quickly. Of course, you're not gonna be guessing and checking how many possible combinations you have for real numbers. Well, infinite. Situation is, how can you get that 2,3 then? Okay, at the beginning I was asking you, there are some methods that work for this one. I remember Ana Lucia says that graphic method, then elimination method, substitution method, you say, and then I tell you something about the matrices. But at the end, those are like the algebraic methods that works for this one. It's not that graphic method doesn't work for in an algebraic way. No, it works. It works, but it works more in the geometry. We're going to explore one exercise of this in geometry. So at the end, the systems of linear equations will be solved by the principles we saw from the beginning. And of course, all that you have to do is like focus in the way to create those equations just like one, working with one variable. Okay, what are the algebraic methods? Substitution. The substitution method will require that you free or leave alone one of those variable expressions. As an example here, in the exercise, the best way will be like leave these x alone. And you can do it subtracting in both sides, or adding, sorry, in this case, adding in both sides the 2y, or just passing the negative 2y to the other side. Having this expression, then you can replace that value of x over here and build now one equation that will work just with one variable. That's what we want, a linear equation with one variable, as you can see it here. As you can see it over here, okay? And at the end, solve this exercise will require that you just pass to the other side. Knowing one variable, you can find the other one just replacing in any of those for the value of the variable you want to, okay? Easy. The elimination method is a little bit more tricky. The elimination method requires that you focus in or look for the way to eliminate one of those variable expressions. Honestly, this is working more with the subtraction of polynomials. But again, like I told you, I'm not gonna focus on this. We're not gonna have the time. And I want that we start exploring the geometry. So for the geometry part, please, if you're in your computer, open a Google window. If you're in your cell phone, well, you cannot like leave the meeting, right? So try to look for a computer, and that way you're gonna participate at the same time, okay? So you're gonna have this presentation when we conclude this class. Don't worry, just try to like copy the main ideas. What are the methods to, or the methods to solve systems of linear equations? Elimination method, substitution method, which are like the principles. You say graphic method and the matrix method. Okay, so probably questions like that. This last set will be like part theoretical, part practical. Okay. We can start now talking about these forgotten area, the geometry, because with this one we conclude a part of the algebra, okay? And of course, we're gonna try to make a connection with those areas. Just let me tell you that geometry that you will develop in those years, you're gonna work with these children, will be focused more into the part of just identify and recognize and name. Those will be like main ideas. There are some principles, but those principles are studied like part of other areas, like part of algebra. And I'm talking about area and perimeter. For example, when you talk about geometry, you start thinking in area, perimeters and area, or volumes, or the shape. But all those are used in different contexts, not as the geometry uses. Those are used like complements of the other areas. So I think that we can start talking about this other part. And that way we're gonna be clear what I'm saying. Geometry, the last part, the forgotten area. And you can see it, I mean, many groups decide to work with geometry. Don't know if you decided because you saw there wasn't many topics over there. I don't know if you decided for that reason. But at the end, it's very interesting because the geometry is one of the oldest areas of math. This is the first thing. Second thing is it's greater than the other one, okay? It's greater than the other one because this one's still growing until today. And it is especially because it's divided in many other geometries. Don't know if you know or if you ever pay attention on what's the geometry that you are teaching, because there are some kind of geometry. If you don't know it, okay, you can start Googling because some questions will be related with this. Okay, let's see. When we talk about geometry, or what do we need to talk about geometry? First of all, describe the geometry that we will study in the second cycle of our national education. And I think of the United States too, it's the same. Determine the type of geometry that we study in the school. Okay, so that's so important. We're gonna describe and then we're gonna determine what is. So when we talk about geometry, what do you know about geometry? What is geometry? I will ask you to describe geometry in 1 or 2 words. So everybody is able right now to participate. So please doing it. Just let me check if I'm recording. Oh yes, I'm recording. So please participate.
Okay, I will describe geometry in one word like shapes.
Like
Shapes.
shapes. Could you write it here in the,
I don't know. I will write it right now.
please? Like Ana Lucia did it. She says angles. Okay. That's what you found, or that's like first thing comes to your brain when you saw geometry. Angles. Okay. Shapes. Shapes and angles. What else? Let's start filling all these, please. Filling with information. Come on.
Relationship of points and lines.
Okay, write it over there. Points and lines. Solids. Orixis writing over there. Size. Okay. Lines and surface. Kelly. Okay. Perimeters. Sides. Anna. Objects like circle, triangles. Leonardo is writing over there. I don't know if well, I don't get it. What do you want to write, Leonardo? There's one text option. I mean, there's like a little T that let you introduce text. If you want to use this one. Lines and surface. Dimensions. Okay. Mauricio, objects like point, circles, and triangles. Someone wrote in the chat, area, Aurora. Okay. Flat shape. Line measurement, surface. Figures. Wow, it's coming like a bingo here. Right? Who guessed it? No, honestly, all those ideas, all those words you have over there, let me erase it. I related with this idea of the geometry. But geometry goes pretty away, and it's not just this. Okay? I'm gonna share with you what you wrote over there. The next slide. And we're gonna keep and save this one, this idea. Okay, don't know if when you like try to investigate for something new, something that you don't know if you look first of all like for the meaning of the. Oh, okay, got it. You say relation of areas and lines and areas. Okay, got it, Leonard. But when you look for something that you don't know if you find out first of all like the meaning of the word. Don't know if someone focused on that part, like find the meaning of the word. Geometry means earth measurement. As I told you, mathematics looks for the answer of these. Measure the world. Always, we're working for this. I mean, you say many of the elements that are part of the geometry that we study. Now, is that geometry that we know? Probably you haven't heard about the geometry you don't know. Okay, that's why you don't know it. Have you ever heard about the fractals, for example? The theory of the fractal? That in those days, in those last 20 years have been growing a lot. If not, okay, we're gonna see then, focus in the next part. And yeah, here's like your screenshot of every of the ideas you gave. So good, so we're gonna be participating like this, so please participate. There are some kinds of geometry that use other mathematics to complete their studies or that model the geometry in a different way. So look on internet, please, for the kind of geometries that exist until today. In this, of course, there are some more, honestly. There are like there are 5, but I'm gonna focus in 4. The 4 that normally Google gives you immediately. So what are those 4 kind of geometry? You can write it over here, no matter if it doesn't like fit in the letter A or in the letter B and the letter C. What matters to me is that you participate. So please start participating over there. Yeah, Google it, no problem. Oritz is trying to write over there. And Lucia is trying to write over there too.
I am using my cell phone, but only appears bolígrafo, not like text. But I'm trying to write non-Euclidean.
Oh, okay. Non-Euclidean. Non-Euclidean. That's one of the geometries. You got it. You have analytic geometry. Couldn't see who wrote it. Analytic in pink. I'm gonna try to.
I wrote it.
Oh, got it.
I-
Non-Euclidean, you say? Okay, your research is so good. You have the hyperbolic. Excellent. Analytic geometry. Oh, you have over there all the geometries. That's so good. Differential non-Euclidean. That's so good. The hyperbolic, it's so interesting. That's part of the non-Euclidean. The projective, okay, that's part of the non-Euclidean too. The elliptical, part of the non-Euclidean. It's so interesting what you find on the internet, right? But let me tell you, that's so huge. These areas, I mean, these ideas of the geometry are very big. Let me do something, and I'm gonna take another screenshot right now of this idea you gave, these ideas you gave, what you found. That's so good. I like it. And let's clean up all those. Oh, you still, but okay, those overlap right now. So hard to see it. But thank you. I mean, you did it so good. We're gonna clear all the drawings and then share with you this screenshot of what you wrote over there. And yes, I mean, you're not far away of what the geometry is. Your research is so good. I mean, Google do all the job right now, right? And it's true. Many of the geometries you say are over there or will be mentioned here. Solid geometry. Okay, solid geometry. Well, it's like a part of the geometry that we normally use in school. And as you can see here, we have like the four geometries that practically have been developed in all those years. Starting with the Euclidean geometry as the first one. Then we work with the non-Euclidean, with Borns practically like for a little contradiction of the Euclidean. So use the elements of the Euclidean geometry to complete a new context. The analytic and the differential geometry are the ones that use other branches of mathematics to complete their studies. So let's talk about the first geometry, the Euclidean geometry. The Euclidean geometry is the most common geometry based on the elements of Euclid. Who was Euclid? Okay, well, say we that study a lot of cultures around Greece, okay, cerca de Grecia, no recuerdo cómo decir Grecia. Okay, and the main idea is that he collects many of the principles and he specified all those in this field of concepts, ideas, theorems, postulates, and axioms that he developed on this book. And you probably will feel that I'm not talking about shapes, lines, solids, measurements, angles, because at the end, all those just were ideas. We're just ideas. We're just simple ideas. So it works behind the principle of three primary elements: points, lines, and planes. The base of the geometry that Euclides proposed are like these three elements, okay? So I don't know. You're getting like main ideas of this geometry. Let's talk about the other type of geometry, the non-Euclidean geometry. In this case, it's just an extension of the, it's an extension of the Euclidean geometry, and it focuses on the relationship made on the planes, and And those planes works differently than the Euclidean geometry. Okay, something that will like help us to understand better. The little graphing that I have over there. And of course, there are like many non-Euclidean. Most of the common ones are the elliptical geometry and the hyperbolic geometry. In the Euclidean geometry, we consider the relationships of the planes working like straightly. When they have like no inclination, they make a straight. No. Now, it's not always like that. And for example, elements or to describe situations that happen in space, for example, we need to use hyperbolic planes. Por ejemplo, el movimiento de un cometa no se puede describir. Una trayectoria de un cometa no es directamente estrecha, a pesar de que si tal vez ustedes alguna vez han visto un cometa, pareciera que va formando una línea recta, pero eso es debido a los astros de luz. Realmente no va haciendo ese movimiento, haciendo un movimiento así como en caída, solo que no lo logramos apreciar. Entonces la hipérbola, la geometría hiperbólica sí lo logra describir. Se lo voy a describir así de manera sencilla. En una se contempla siempre un plano estable, un plano que podría decirse está derechito, está planito. Pues. En otra se contempla un plano que se curva hacia adentro. Y en otro un plano que se curva hacia afuera. Ahora, hay otras geometrías elípticas. Un plano que se curva indefinidamente, un plano que se curva con una trayectoria rectilínea, y bueno, ahí aparecen un montón de nuevas geometrías y nuevas propiedades. Pero en sí, la geometría no euclidiana es romper la idea de que solo los planos planitos existen. Pues los planos así como nosotros no los podríamos imaginar, existen. Y no es cierto, existen muchos más. Vaya, les pongo un ejemplo. Cuando ustedes hacen su cama, esperan que quede todo estrechamente planito, ¿verdad? Y eso sería parte de la geometría euclidiana. Si ustedes le hacen así a la sábana, cuando la quieren extender, bueno, justo en ese momento que se empezaron a hacer como varias olas con la cobija, con la sábana, bueno, esos serían los planos de la geometría no euclidiana. Okay, that's like a simple idea to understand what happened with this one. What happened with the other one? The analytic geometry. The analytic geometry was practically made by Descartes. Descartes was a French mathematician. Well, not just mathematician, philosophy. I think works in politician too. And he proposed some problems of the Euclidean geometry in this context, the context of points in the coordinate plane. So essentially, the analytic geometry used elements of algebra and move those to something simple to describe these problems that we're having in the Euclidean geometry. Tiempo atrás no se enseñaba tanto álgebra, no se enseñaba tanto resolver ecuaciones, no se enseñaba tanto encontrar áreas y figuras, no, se enseñaba geometría. Y no se enseñaba la geometría como la estudiamos hoy. De hecho, vamos a ver cómo se enseñaba con una pequeña muestra que tengo ahí, una pequeña demostración. So, at the end here, the analytic geometry makes a connection between the algebra and the geometry. Understanding this connection like the problems of geometry, like the problems we have in algebra, polynomials, functions, equations, formulas, numbers and variables. And that's so interesting. So that's what Descartes made. A little observation here. In the differential geometry, we can see how the non-Euclidean geometries works with all those elements of algebra, of course, going a little bit deeper. So here we go, and the main idea with this differential geometry is describe some situations, sorry, quiero decir fenómenos, no me acuerdo de la palabra en inglés. Some situations that works based on these, and as an example, those shapes that we know, that three-dimensional shapes, they come from the differential geometry. Those are called revolution solids. And it is because what happened when you have, I mean, everything starts with a simple question. What happened when you have a rectangle and you start to rotate this as many times as you can? What shape will make?
Cylinder.
It will make a cylinder, okay? It will make a cylinder. And all those shapes that born from that simple idea, okay, what happened if you have like a circle and you start to rotate this one as many times you can? You're gonna make a sphere.
Here.
Exactly, you're gonna make a sphere. And all those shapes comes from there, from the idea of rotate a simple 2D shape that then becomes a 3D. Okay, and this geometry use those elements. So what elements? Elements of calculus that let you describe this. So the differential geometry at the end is one of the hardest. Honestly, it's most studied in those things like, bueno, lo voy a decir así, el viaje aeroespacial, por ejemplo, en la matemática del boom, que fue la matemática de los años 60, ustedes saben, el pleito que hubo entre, o bueno, no el pleito, sino esa batalla tanto teórica como ilustrativa, como científica, de llegar a la luna en los años 60, bueno, desató bastante conocimiento en esta área. Y de hecho es una área que sigue creciendo hasta el día de hoy, porque seguimos intentando llegar ya no a la luna, sino ahora queremos llegar al planeta Marte, ¿verdad? Al planeta rojo. Entonces, esto sigue creciendo. Y mucha de la geometría que se utiliza para hacer construcciones nace aquí. O sea que los ingenieros tienen que saber bastante de geometría diferencial. Okay. What is the geometry that we study in the school then? What do you think? Now here I want to hear like your idea.
The Euclidean geometry, because it's the most basic one.
It's the most basic one. What else? I mean, it's just this one? Because my question is, what geometry? Yeah. Study in school. I'm agree with you. You say Euclidean. Okay, don't know if someone else thinks something different. Probably non-Euclideans. I don't know if you study like rectangles that goes this way. This will be like a rectangle in non-Euclidean geometry. I mean, still being the rectangle as it's that page, but if we start like moving it, it becomes like non-Euclidean. Do we study shapes like this in school? No, right? So non-Euclideans are not part of the school. What about the analytic geometry? Don't focus just in shapes.
Mister,
¿Ya, Mauricio?
la geometría es un tema que casi no se estudia en las escuelas. No sé, creo que a las personas les da miedo comenzar y tal vez si se llegara a estudiar, tal vez sería, no sé, la geometría de este personaje, Euclides. Euclides, ajá, tal vez lo más básico, nada más, no sé, tal vez como, por ejemplo, cuando yo recibí clases de geometría que estaba en primaria, ok, me enseñaron a sacar base de un cuadrado, base de un triángulo, base de un rectángulo, el área de un círculo. Y ya cuando llegamos al pentágono, dijo el profesor, bueno, ya esta solo les voy a enseñar la fórmula, porque ya aquí es meternos a cosas que no, dijo. Entonces, les puedo dar hasta las fórmulas para sacar áreas de hexágono, heptágono, octágono, pero ya esa ya no las vamos a ocupar. Algo así como, siéntanse felices con que pueden sacar el área de un triángulo, sí, el área de un círculo, de un rectángulo.
Es que lastimosamente, como usted lo dice y como se los decía desde el inicio, Miren, la geometría es una de las áreas más grandes de la matemática, pero es una de las que menos se enseña. Y de hecho, el hecho de hacer la parte hace que pensemos que la matemática es mecánica y que la matemática solo son sumas, restas, multiplicaciones y divisiones. Les diré que la geometría es una de las áreas que permite desarrollar la lógica y algo que creo que todo mundo quiere desarrollar en sus estudiantes, el pensamiento crítico. Y justamente la geometría, déjenme decírselo sin mentirles, es la mejor herramienta que permite hacer esto. Ya vamos a ver por qué.
Por eso hay diferentes, perdón, licenciado, por eso hay diferentes juegos y que, bueno, no sé si entra acá cuando los niños están pequeños, que los bloquecitos de madera que tiene forma de círculos, triángulos,
Sí.
ok, esos, por ejemplo, el juego del Tangram, que ellos puedan armar figuritas con las piececitas del Tangram,
Las 7 piezas,
también.
¿sí?
Ajá, también son para que ellos se desarrollen el pensamiento.
Intelecto, el pensamiento y el intelecto. Y eso vean que ni importancia le damos a veces y de un solo, a veces en vez de empezar con un juego así, empezamos enseñando ya de un solo el 1, 2, 3 y decimos este es el 1, este es el 2, cuente y haga. Entonces dejamos de lado esta área y sí, les voy a decir que solo son dos las que normalmente estudiamos. Estoy de acuerdo, la geometría euclidiana y la geometría analítica. La geometría analítica es la que trajo todos los problemas que surgieron en la geometría euclidiana al ser esta muy abstracta a un papel, por así decirlo, a un plano concreto, el plano cartesiano. Entonces, son esas dos las geometrías que nos van a interesar y de las que vamos a tratar un poquito, enseñándoles tal vez unos pequeños ejemplos de ellos, ¿verdad? Con esto terminaríamos entonces la clase y lo referente a la temática de la clase, con esto que vamos a ver ahorita. Me voy a mover a un open board para tener un poquito más de, ahí está, de movimiento y vamos a hablar entonces de esta geometría euclidiana y de la geometría analítica, esperando que el tiempo que queda, que son casi 20 minutos, pues me dé, ¿verdad? Si no da, pues tendré que subirles este recurso completo, pero sí, de manera rápida me gustaría que vieran qué era en sí la geometría y qué es en sí hoy la geometría, porque nos enfocamos honestamente ni en la geometría euclidiana, nos enfocamos más en la geometría analítica, en lo que enseñamos, y no es culpa de ustedes, no es culpa de ustedes, es lo que está en el currículo. No se enfoca mucho en lo que realmente la geometría es y se deja como un área bien allá botada porque se piensa que no sirve para nada, pero bueno, tiene muchos usos y la verdad es que va creciendo cada día más. Y el principal uso es que nos ayuda a pensar de manera lógica y concreta. Okay, so I'm going to describe right now Euclidean geometry. Look, Euclidean geometry based on 5 axioms or 5 postulates. I don't know if you remember what's axiom or postulate, or if you ever heard that word before. Who can tell me what is an axiom or a postulate? Who can tell me what's this? Axiom or postulate? Okay, no any idea. Axioms and postulates are truths that just have to be accepted, okay? It's not a truth like the square root of 4 is 2. No, that's something that you can prove. There are truths that you have to accept, like as an example, a square have 4 sides. Well, that's more a definition. What would be a postulate? Through 4 points that are non-collinear, that are non-collinear, you can create a quadrilateral. Okay, this is a postulate. You're gonna have 4 points. You can imagine those not making a line. I mean, 4 points not working like this. 4 points probably working like that. And the shape that you can create closing this will be a quadrilateral. As you can see. Okay, so this is a postulate. It's a truth that you have to accept because it's gonna work always, every time. Now, there are 5 basic postulates that Euclid works on. Honestly, I'm just gonna focus in 1 or 2 to show you like the main idea of why at the end in geometry you think about lines, shapes, angles, okay? Because it's like the main idea. So based on those postulates, you can create theorems, which are truths that can be proven, or definitions that are truths that can be seen. Postulates, truths that have to be assessed. Axioms, the same. Theorems, truths that can be proven. Definition, truths that you can see. And why I'm saying truth, okay, ustedes pues han leído un poquito de filosofía, creo que ya llevaron filosofía, me habían comentado. Leyeron un poquito de filosofía. Los griegos, ¿a qué se dedicaron cuando llegaron ya a la cúspide de su civilización? Se dedicaron al ocio digno. ¿Y qué era eso del ocio digno? Bueno, estar investigando realmente dónde podían encontrar cosas que demostraran la verdad. Y ellos entendían la verdad como todo lo que podíamos ver, y palpar, pero algunos filósofos griegos se enfocaron en cosas que no podíamos ver y palpar. Sin embargo, existían, porque ellos veían figuras geométricas en la realidad, una en sus construcciones, otro en las civilizaciones que estaban alrededor. Entonces tenían que buscar la forma de entender eso. Y justamente eso hizo Euclides con su libro, el libro de los elementos de Euclides. And that's practically what we teach today, but not as he have it, right? Something that borrows from theorems are like sub-properties, and those properties are called corollaries. Now, what is how is the Euclidean geometry process? The Euclidean geometry process is deductive, and it's based on the definition, on the theorems, and on the postulates to make math proofs. What is a math proof? Okay, I'm going to show you one math proof later. A math proof is write statements and in order to create a new property or to propose a new property. Okay, so that's like the main idea of the Euclidean geometry. It's like create properties, but prove those properties with what? With the field of all the knowledge that they create based on the 5 postulates of Euclid. So there are some basic symbology that we should know, and if we don't know it, it's going to be so hard. For example, a point considered as a minimum idea of the minimum, not shape, minimum inclusively. This is not a good representation of a point. A point is just a location at the end. It's like the minimum part of something in other sciences. It's like the atom. What is a line? A line is a set of points that are working in a collinear way. A plane is a set of points that are working in a non-collinear way. So we can represent points with a letter A. We can represent lines using 2 points of the line. For example, A and B. And we can call this one like AB line. Don't know if you ever seen that notation. I think you're gonna see this notation in your books. Plane, we can talk about a plane just with a capital letter, but we have to specify that it's a plane. Plane E, for example. From these 3 basic elements that are the 3 basic elements that Euclid proposed, borns all the geometry that we have been working, the geometry of the circle, the geometry of the solid shape, the geometry of the triangle, the geometry of the squares. Okay? Something that I have to tell you is that with these basic symbols and with this idea of the postulates, axioms, and properties, that geometry focuses in solve problems related with congruency, existence, and define new elements of geometry. Remember that at the end, mathematics inside itself starts to solve problems itself. So I want to tell you like how to, in this case, how to name some elements. For example, in a shape that is made of segments, you can name each of the sides, that is a segment, focusing the points that describe it. And in this case, it will be a little bit like the same of the line, just that in a line, okay, you show this on the top expression. I mean, on the top, you show like a line. In a segment, no. In a segment, you just show like a part of this line, but not with the arrows. An angle, what happened with an angle? Don't know if you remember how to name angles in geometry, or if you ever do it. For example, how can I name these angles?
Angle AB.
AB, okay, AB will be more for a side. In an angle, you have to use all the elements that are needed. In this case,
I would be,
mhm,
all right, A, C, B.
excellent. That's one way. A, C on the middle, and B over there to say that you're talking about this. If you say angle ABC, okay, then you're talking about this one. On the middle, always you're gonna have like the vertex of the angle. If you don't remember, angles are made by the intersection of two rays, and they make an opening. The opening they make is the angle, but those rays have a common endpoint. So for example, to name this one, like you have it, C over there, A over here, B over here, which means then that I can name it like BCA, and those are like the same, okay? A shape like a triangle, it can be named by requesting the shape you're talking about and the points that make this one. What happens if you have a rectangle? You have to focus in the points it has and call it like this, as you can see. So those are like basic ideas we need to focus in the part of the geometry. And let me tell you that in geometry matters a lot, the vocabulary. So we cannot say part of a triangle. No, we can say segment of a triangle or triangle side, which at the end is a segment. You cannot say the inner part of a triangle. No, we have to talk about angles, and the same with the shape. Here I have two of the postulates that Euclid proposed in his book. And practically based on this one, we can start creating all the shapes that we know. So one of the postulates says, through 2 points pass exactly one line, and this line is inside of a plane. And it's true. I mean, sorry, is it possible that I draw another line that passes through those points? If I focus in to use this one, okay, let me do it better. There he is. I mean, there is just one line that will pass through those points. Is it possible to pass another one? No. If I ask you to tell me how many lines passes through 1 point? How many lines passes through 1 point? Just through one.
Many?
Many. Many.
Infinite.
As many as you want. But if I ask you, how many lines will pass just through 2 points? Just one. So those elements are so important. As you can see, it's a truth that we have to accept. No hay nadie que venga aquí a poderme decir que voy a refutarle eso. Okay, so that's like the main idea. What happened with another of those 5 postulates that he based all the geometry we know and we teach? Through 3 points, pass exactly a plane. And that plane is in the space. If I join the segments that I can, or if I close these points, I mean, I will create like the basic shape that everybody knows as a triangle. And this is a 2D shape. And these 2D shapes exist in the 3D world or not. I mean, it's the main idea. This is 1-dimension shape that exists in a 2-dimension shape. So then this is a 2-dimension shape that exists in a 3-dimension shape. Do you think we live in a 3-dimension world? Or do we live in the 4-dimension world? Realmente vivimos en un espacio cuatridimensional, si no lo han analizado. Somos seres tridimensionales, pero vivimos en un espacio cuadridimensional. ¿Cuál es esa cuarta dimensión? El movimiento. Bueno, realmente es el tiempo, porque sin el tiempo no habría movimiento. Entonces, nosotros realmente somos seres cuatridimensionales. No, somos seres tridimensionales que vivimos en un espacio de 4 dimensiones. Bueno, son cosas bien, pero no vamos a hablar de eso. Creo que alguien, no sé si alguien quiere apuntar algo. No, ok. Bien, entonces tenemos 2 ideas básicas y déjenme decirle cómo era la geometría que de hecho se enseña, se sigue enseñando un poquito de esta geometría, pero cómo era la geometría que se enseñaba antes. Bueno, voy a hablar en español porque ya nos quedan 7 minutos para hacer un poquito rápido. Me gustaría enseñarles esta parte de la matrix, pero voy a enfocarme luego en la parte analítica de la geometría. Se las voy a dejar ahí. Se las voy a dejar ahí para que la vean ustedes cómo se desarrolla. Y esto que se desarrollaría aquí es la geometría que deberíamos de estar enseñando. Sin embargo, no se le da importancia porque no se le ve el uso. Bueno, el uso es bastante amplio en el sentido de que desarrolla creatividad, desarrolla un montón de aspectos que dejamos por alto. Por ejemplo, ¿qué era lo que se enseñaba en la geometría antes? Se enseñaba a construir y encontrar definiciones a través de simples construcciones con regla y compás. Déjenme decirle algo. En la geometría que los griegos utilizaron, no existía el compás y la regla que utilizamos hoy como tal. Bueno, ellos trabajaban con una cuerdita y con eso hacían los círculos, con eso hacían la medición de los ángulos, con eso hacían la comparativa que, por ejemplo, yo les voy a mostrar ahorita. ¿Habrá alguna forma de encontrar el punto medio de este segmento? Dirán ustedes, sí. Hoy tenemos una regla que nos ayuda a resolver eso de inmediato. Y utilizando las medidas, nosotros podemos determinar cuál sería la mitad de este segmento. Si sabemos que mide 8 centímetros, pues la mitad debe estar aquí, ¿verdad? Ahora, qué bien por nosotros que hoy tenemos todas estas herramientas que nos permiten encontrar ese punto medio o ese valor a la mitad. Pero los griegos no la tenían. Los griegos no tenían una regla, con estos numeritos y todo, ¿no? Ellos nada más tenían el compás y una regla, sí, pero sin numeritos. Entonces, ¿cómo ellos encontraban el punto medio? Bueno, pónganle ojo. Utilizando el compás se puede hacer. Ubicaban uno de los extremos y el otro para completar por así decirlo, todo el segmento y lo extendían. Lo extendían tanto hacia arriba como hacia abajo. Y esto lo hacían no solo con este extremo, lo hacían con ambos extremos. Entonces procedían de manera similar con la siguiente parte o con el siguiente extremo y encontraban algo. Un punto de intersección. Bueno, no solo uno, 2. ¿Por qué ocupaban 2? ¿Qué dijimos al inicio? Por 2 puntos pasa. Por 2 puntos pasa una recta. Lo dijimos al inicio, ¿verdad? Y vean ustedes que si yo marco estos 2 puntos de intersección, lo que espero realizar es unirlos por medio de una recta. Vamos a marcarle en verde, un poquito más delgada. Unirlos, y si ustedes se fijan, ¿por dónde pasa esa recta exactamente? Y con más exactitud incluso que con lo que yo hice aquí. O sea, aquí hay un error humano al utilizar esta herramienta. Con lo que ellos propusieron, no. Había exactitud exagerada. ¿Qué es lo que pasa exactamente? No sé si lo lograron ver. O sea, ¿qué sería este punto en donde se intercepta esta recta que está en verde y mi segmento? ¿Qué sería? Es el punto medio, ¿verdad? Y si ustedes ven ahí, todo se hace en base a una herramienta que, bueno, hoy en día creo que, no sé si ustedes se han enfocado en cómo se utiliza el compás en alguna de las clases que han dado de matemática enfocada a la geometría. No le damos importancia. Y miren qué interesante y cómo se construye esto. De hecho, ustedes van a tener una tarea en la que posiblemente lo hagan a mano o si quieren utilizar herramientas online como la que yo les sugiero, en la tarea para construir un triángulo isósceles. Esta construcción que acabo de hacer yo ahorita les puede servir. Esta recta que acabo de descubrir yo ahorita les podrá servir a construir un triángulo isósceles. Voy a mostrar ahorita cómo construir un triángulo rectángulo, por ejemplo. Y todo es en base a los postulados y las propiedades que ellos propusieron. A esta recta que acabo de encontrar se le llama mediatriz. Y es una recta perpendicular que a la vez corta un segmento a la mitad. ¿Y qué es eso? Bueno, eso es nada más una de las tantas definiciones que Euclides propuso en base a estas 5 verdades. Bueno, aquí solo les estoy mostrando 2, ¿verdad? Y se vuelve bien interesante. Entonces, voy a construir así rapidito porque ya no ganó el tiempo, lástima, para que podamos profundizar un poquito más en esto. Pero solo quiero que vean cómo era la geometría que se estudiaba antes. Ya se nos está olvidando esta geometría. Si yo quisiera construir un triángulo rectángulo, por ejemplo, tendría primero que buscar el punto medio para generar así lo vamos a hacer rápido, generar así un círculo luego que me va a ayudar a construir ese triángulo rectángulo. Desde luego, y dirán ustedes, ¿y eso para qué sirve? Bueno, la construcción geométrica desarrolla bastante la creatividad. Y creo que hoy en día eso es algo de lo que estamos tratando de enfocarnos mucho, ¿no? Entonces, si yo tengo el punto medio, lo voy a encontrar aquí rapidito, de esta expresión, o de este segmento, estaría aquí. Obviamente no hice la parte de abajo, pero haciéndola se encuentra ese punto medio. Ahí está. Podríamos luego con el mismo compás crear un círculo que tenga centro ese punto medio y extremo uno de los mismos extremos del segmento. ¿Por qué? Bueno, le explico la lógica que está detrás de esta construcción que vamos a hacer ahorita. Vamos a hacerle en azul. En un semicírculo, en cualquiera, y esto es otra propiedad, si nosotros marcamos uno de los puntos de este semicírculo y lo unimos a los extremos de este segmento que acabo de mover, vamos a crear un ángulo recto. A nosotros lo que nos interesa es crear un triángulo rectángulo. Bueno, pero los triángulos rectángulos están formados de ángulos rectos. Vean qué interesante lo que voy a hacer ahorita. Y ustedes podrían hacerlo también. Marcando cualquier punto. Vamos a ver, este de acá. Independientemente cualquiera que yo marque. Lo que se va a generar aquí es un ángulo de 90 grados. ¿Qué es esta figura entonces? Que tengo marcada en negro. Es un triángulo rectángulo. ¿Qué pasa si lo hubiésemos decidido poner ese punto en cualquier otro lugar? Solo para que vean ustedes. Si se me hubiera antojado a mí ponerlo por acá, por ejemplo. Siempre se va a formar un triángulo rectángulo. ¿Y esto por qué lo sé? Ok, porque son propiedades que los griegos ya habían determinado antes. Ahí se ve, miren, es de 90 grados. De hecho, aquí tengo esta herramienta, que esta herramienta no existía en aquel entonces, para poder medir si realmente es de 90 grados o no. Poniéndolo lo más correcto posible, nos damos cuenta que sí es un ángulo de 90 grados. Donde sea que tratemos esto, siempre va a trabajar. Entonces, de eso se trataba la geometría de aquel entonces. ¿Y qué hacían ellos? Ok, por medio de figuras y por medio del rigor matemático, creaban demostraciones matemáticas que al final describían la matemática de esta manera. Ahora, ¿cuál es el problema? No todos la entendían. ¿Qué hizo René Descartes? La llevó a un plano cartesiano, bueno, por eso se llama plano cartesiano, o a un plano coordenado, donde todo el mundo lo pudiera entender. Y de hecho, muchos problemas de la geometría, por ejemplo, aquí no podríamos hablar de la medida de un segmento. Podemos comparar si un segmento era más grande que otro. ¿Cómo? Con el compás. Podemos comprobar si el punto medio de todos los segmentos me generaba alguna relación en el triángulo. Y de hecho sí, se genera algo que se llama ortocentro con eso. Pero al final la geometría aquí quedaba muy teórica. Entonces alguien la volvió más práctica. Por eso estas dos geometrías van de la mano y una no se complementa con la otra. La geometría analítica sí se complementa con la geometría euclidiana. Y con esta geometría, bueno, ustedes ya dijeron, es donde se grafica. Por ejemplo, ¿qué puedo hacer yo con estos dos puntos? Solo para enseñarles una idea simple. ¿Qué puedo hacer yo con estos dos puntos? Y me estoy pasando el tiempo, me disculpan, va a ser rapidito. Puedo generar una recta. ¿Qué puedo hacer yo con los otros dos puntos que están marcados ahí en azul? Puedo generar
La recta que...
otra recta, ¿verdad? Ahora, miren lo interesante. Estas dos rectas, tanto la recta en verde como la recta en amarillo, me están generando algo a mí. No parece. Pero ellas me están generando un sistema de ecuaciones lineales. Sería este el sistema de ecuaciones lineales. Claro, algunos dirán, pero ¿y por qué no simplificó un poquito más ahí? Está bien. 5 sobre 5 es lo mismo que 1. 2 sobre 4 es lo mismo que 1 medio. 1 medio de x menos 2 para la primera ecuación y 1x más 5 para la otra. Perfecto. Bueno, creo que sería negativo 1 porque va hacia abajo. Acá. Negativo 1. Esto es un sistema de ecuaciones lineales. Gráficamente, el sistema de ecuaciones lineales se puede resolver encontrando el punto donde ellas dos interceptan. Ese punto donde ellas dos interceptan corresponde a unas coordenadas, ¿no? Y esas coordenadas trabajan con un eje X y un eje Y. Es decir, una coordenada corresponde a X y una coordenada corresponde a Y. 1, 2, 3, 4 y 1. O sea que la solución de este sistema sería 4,1. De manera gráfica, claro está. Ahora, ¿de dónde proviene esto? De la geometría. La geometría y el álgebra son las áreas que nosotros, pues, prácticamente enseñamos a lo largo de todos estos años, pero las estamos enseñando de otra forma. ¿Por qué? Porque no las podemos enseñar meramente como se estudiaron o como se descubrieron. Sería un problema. Por eso ustedes hoy hablan de triángulos, hablan de lados, hablan de ángulos y no hablan en sí de todo este montón de propiedades de utilizar el compás para descubrir qué eran, ¿verdad? Me disculpo porque les robé 5 minutos, pero voy a dejar la clase hasta acá. Recuerden que les voy a subir todos estos recursos. La evaluación va a ser de lo que estuvimos estudiando tanto ayer como hoy. La parte de los polinomios, la parte de ecuaciones, la parte de identificar qué tipo de ecuación es, lo que está detrás de eso. Por ejemplo, si tiene grado 5, cuántas soluciones se esperan tener. Cositas así son las que van a venir en el examen. Y bueno, esto ha sido todo el curso. Creo que lo dejamos hasta acá. Solo queda pendiente su proyecto. Pues espero lo hayan disfrutado del curso y la verdad es que falta mucho más del curso. Honestamente, el tiempo se nos quedó corto. Era intensivo, se tuvo que diseñar así, ¿verdad? Y
Mr.
bueno,
Thomas,
dígame.
I have a question with the last assignment in the forum, number 4.
Ajá.
Could you like explain please, because I don't really get the instruction of the forum. I don't know if we have to choose just one of the, how you say this?
Of the
Yes.
theorem. Ya. Ok, lo voy a explicar así rapidito. Solo déjenme, abro los documentos. Ok, la primera parte, no sé si lo están viendo. No, ¿verdad? ¿Ahorita?
No.
¿Lo estaba
No, yeah.
cargando? Ok. La primera parte, si ustedes se fijan, de la asignación es hacer una construcción geométrica. Ahorita acabo de hacer 2 construcciones geométricas. De hecho, aquí yo les dejo el website donde sale el resultado final, pero me gustaría que ustedes lo hicieran, que lo intentaran hacer. Esto es un sitio web que les permite a ustedes incluso trabajar con el compás de manera intuitiva, así como lo hice yo en esta OpenBoard. Si alguno tiene OpenBoard, pues puede hacerlo ahí. La construcción del triángulo isósceles es muy similar a la construcción del punto medio que yo les acabo de hacer. O sea que prácticamente ahí la tienen. Solo habría que construir un triángulo a partir de eso. Para la parte 2 es en el plano cartesiano con un máximo de 10 unidades para arriba, 10 unidades para abajo. Creo que el plano cartesiano lo hemos visto antes, ¿verdad? Y si no, pues yo les voy a dejar este plano cartesiano, que ustedes lo vieron ahí, donde estaban las dos rectas graficadas. Van a buscar ustedes la forma de construir por medio de puntos, por medio de coordenadas cartesianas, 5,2, 3,1, un trapezoide o un rombo y un rectángulo, porque aquí solo van a seleccionar dos. Sería llevar una de estas figuras al plano cartesiano. Eso es todo. Hay sitios web que lo hacen por ustedes. Me gustaría que lo hicieran ustedes aquí, por eso no les puse acá. Ahora, para ello tienen que investigar primero qué es un trapezoide, qué es un romboide, qué es un rectángulo. ¿Ok? Pero solamente sería decir, o bueno, graficarlo en el plano cartesiano, pues especificando cuáles son las coordenadas para cada uno de los puntos. Eso sería la tarea. Respecto a la otra asignación, que es el foro, en el foro, y aquí sí se pone un poquito interesante, verán ustedes parte del libro de los elementos de Euclides en un sitio web, en un PDF que les recomendé por ahí, y ahí están todos los teoremas. Lo que van a hacer, ya que la participación del foro es individual, enfocarse en alguno de todos esos teoremas. Por ejemplo, hay uno que dice ahí, en un triángulo isósceles, los lados que no corresponden a la base son congruentes. ¿Qué significa eso? Que los lados del triángulo isósceles pues miden lo mismo. Quieran ustedes buscar un ejemplo que muestre un triángulo isósceles con los dos lados que midan lo mismo. Lo que más me interesa a mí es que ustedes lean e interpreten el teorema propuesto por Euclides. Vale, voy a buscar aquí ahorita alguno de esos
Ok,
teoremas.
entonces sí es como ilustrar, ¿verdad?
Solamente ilustrar el teorema, así es. No, no es que lo van a demostrar o buscarlo o explicarlo, los orígenes y eso. No, solamente es mostrarlo. Y de hecho es bien sencillo, ¿verdad? Ustedes verán ahí que hay bastantes elementos que les pueden servir, como algunas definiciones, algunas propiedades. Y eso es lo que me interesa que vean ustedes en este foro número 4. Perdón, no sé si lo están viendo, creo que no vi compartir toda la pantalla. Ahorita lo hago. Mejor así. Aquí está, foro número 4, y aquí les aparece un sitio web. Y de hecho un documento que tiene los teoremas. No hay que leer todo esto, no es necesario, pueden leerlo. Habla un poquito o describe un poquito lo que propuso Euclides, pero en sí, lo que me interesa a mí es que nos vayamos a la parte que dice teorema, tomemos uno y lo ilustremos. Eso es todo. Aquí aparece uno. Si dos rectas distintas se intersectan, entonces su intersección es un punto único. Bueno, esa yo la hice, ya no la pueden hacer. Esa yo la hice en el plano cartesiano. Ustedes ya vieron, si se intersectan, entonces el punto es único. Si dos rectas distintas se intersectan, entonces existe un plano único que los contiene. También ya lo hice. Partan del siguiente. Si dos figuras convexas y su intersección no es vacía, entonces la intersección es convexa. Si no entienden qué es convexo, tienen que investigar qué es convexo. Pero hay más. Vaya, propiedades del triángulo isósceles. Los triángulos, en todo triángulo isósceles, los ángulos opuestos a los lados congruentes son congruentes. Esto está fácil de demostrar. Solo que hay que interpretarla como en una figura. Eso es lo que necesito que hagan en el foro. Dos ángulos opuestos por el vértice son congruentes. Bueno, hay que buscar qué son ángulos opuestos. Les aseguro que ponen ángulos opuestos y ahí les va a aparecer la respuesta. Corolario, en un triángulo equilátero, un triángulo es equilátero, sí, solo sí, sus tres ángulos son congruentes. Y esta es la geometría euclidiana. Miren. Por un punto de una recta contenida en un plano dado, pasa una única recta que es perpendicular. Hay que mostrar dos rectas perpendiculares que pasen por una recta perpendicular que pase por ese punto. En un triángulo isósceles, la mediana compartida de los lados, de hecho, esta es la que iba a hacer una demostración. No pedirles que hagan la demostración, solo la ilustración de esto. ¿Cómo es eso? ¿Y por qué los estoy poniendo a hacer esto? Bien, porque en la geometría que ustedes enseñan en primaria, ¿verdad? Y digo ustedes porque ahorita algunos de ustedes tienen esa responsabilidad de enseñarla. No nos enfocamos en el vocabulario y eso es la clave de la geometría, el vocabulario. Si no lo manejamos bien el vocabulario, pues difícilmente enseñamos geometría. Y aquí aparecen un montón de teoremas. Ustedes los tienen que leer, interpretarlos y buscar una imagen que encaje a ella o hacerla, la pueden dibujar. Yo preferiría que la dibujaran. No hay ningún problema. Pueden utilizar OpenBoard si ya lo descargaron para hacer esa parte. Incluso pueden utilizar las herramientas como le enseñé yo ahorita. En el OpenBoard todo eso aparece, por ejemplo, el compás y todo eso aparece aquí. En las opciones que ustedes tienen acá, en una parte que dice aplicaciones. Normalmente aparece aquí así y buscamos la parte que dice aplicaciones. Ahí aparece, miren. Un compás, un transportador, una regla, bueno, una escuadra, una regla. Y aquí tenemos todas las herramientas para hacerlo de manera intuitiva. La geometría, como les decía, pues es bien completa. Y ustedes pueden ver acá, pues, una pequeña prueba de ello. Les adelanto un poquito. ¿Qué tendrían que hacer para responder la primera parte de la tarea? Bueno, podrían extender este punto, esta recta, perdón, más arriba, seleccionar un punto cualquiera y luego cerrarlo. ¿Qué se va a generar? Ya saben ustedes la respuesta. No sé si hay alguna otra duda. ¿Tenemos alguna otra duda? Sí, qué lástima que no dio chance de ver una demostración, pero bueno. ¿Alguna otra duda? Si no, nos podemos empezar a retirar, no hay ningún problema.
Solamente agradecerle, licenciado, por las clases y por toda la enseñanza.
No, excelente. Yo más bien agradecido con ustedes por su participación también, porque han sido bien fortuitas. Y la verdad es que en estos cursos lo que se quiere es eso, enriquecerlo por medio de la experiencia, no solo del profesor, sino de ustedes, porque ustedes también pues tienen experiencia con la matemática, tal vez enseñándola. Me gustó que algunos buscaron más y lo felicito, Mauricio, porque en su grupo, bueno, lo que recuerdo es que investigó, por ejemplo, de las teorías de Van Hill, las teorías de la enseñanza de estas áreas de la matemática. Y de hecho podemos hacerlo, y de hecho se va a hacer más adelante en otro curso que se llama Didáctica de las Matemáticas, para el cual algunos de los recursos que nosotros hablamos acá, por ejemplo, el hecho de haber visto cómo se nombran estos elementos, serán indispensables para tratarlos después en esa otra clase, ¿verdad? Bueno, como les había dicho también, pues muchas gracias y mucho gusto, ha sido un placer, espero tener la oportunidad de volverlos a tener en otra clase. Y bueno, hasta aquí dejamos la clase por hoy entonces. Solo quedaría pendiente las evaluaciones, que yo sé las van a hacer muy bien, y el proyecto, ¿verdad? El proyecto sí es para mañana, las evaluaciones tienen fecha límite el martes, si pueden presentarlas antes, por favor, para así terminar su nota y subirla al sistema el martes y así sepan si ya tienen abierto el chance para las siguientes clases que esta abre, ¿verdad? Lo dejo hasta acá entonces.
Y la prueba también, Lick.
Hey, sí, cierto, la prueba. Claro, la prueba, no se nos puede olvidar.
De 8 de la mañana
a 11. Va a estar dispuesta. Eso sí, si usted la abre a las 8, tiene hasta las 9 para resolverla, porque se cierra automáticamente en una hora. Bueno, sí. Si no hay más consultas, pues qué gusto, qué placer, y sería hasta la próxima, si Dios lo permite.
Nos vemos en estadística, mister.
Ojalá, Dios mediante.
Muchas gracias, mister.
Bueno, nos vemos, buen día.
Muchas gracias, mister. Muchas gracias, buen día.
A ustedes, muchas gracias, buen día también.
Gracias, Lick, por todo.
Gracias a usted también por sus participaciones.
Muchas gracias, Lick, por todo.
Igualmente, Mayra, muchas gracias.